right, so we are in section 8.4. We're going to talk about the binomial theorem today. So the binomial theorem, what we want to do is we want to figure out a way to use what we know now about sums, about adding things up, to come up with a way of expanding an expression. So first off, what is a binomial? It has something to do with 2, right? So a binomial is a polynomial with 2 terms. So what we want to do is come up with a way of, find a formula for expanding a binomial raised to a power. So we want something like x plus y, where x and y are some variables or some numbers, to the n power. And we want something a little easier than multiplying all these parentheses together n times. So what I want to do is write down a few of these expansions, and hopefully we can start to see some patterns. So x plus y to the 0 power, what's that going to give us? 1. Anything to the 0 power is 1. And I'm going to write over here we have one term. Our one term is just 1. Now let's look at x plus y to the first power. Well, that's just going to give us x plus y. And we have 2 terms. Now let's look at x plus y squared. And we multiply that out. I'm not going to make us do that, but we get x squared plus 2xy plus y squared. And we get 3 terms. Let's do x plus y to the third. Sorry, x plus y to the third. And when we multiply that out, we get x cubed plus 3x squared y plus 3xy squared plus y to the third. And we get 4 terms. X plus y to the fourth. These are getting a little longer now. We get x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. And we get 5 terms. And we could keep going, but I think we can start to see a couple of patterns here. So does anybody notice any patterns between these, between our exponents, with what we have here? So what are you saying there, Chad? We have n plus 1 terms. So each of these we have n plus 1 terms. This is the 0 power, we get 1 term. 1, we get 2 terms, so we have n plus 1 terms. Any other patterns we see?
The numbers in front of the variables are symmetrical.
So we have this symmetry here. We have a 1 and a 1, a 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So the powers of x and y in any term are the same as n. So here n is 2, here we have x squared, here we have x and a y, so a 1 and a 1, that gets 2. Same thing here, these two, x squared and y, so we get a third power, so the sum of the powers of any term, we end up with n. Yes?
We're going to be using the triangle.
So we have the symmetry of the coefficients, we have this relationship with the terms and the exponent, and we have this relationship with the exponent and the powers in each term. So what mathematicians did was they said, well, this looks like a pattern. Let's try to find a rule for the pattern. Well, that rule for the pattern is called the binomial theorem. So what I want to do is write out the binomial theorem. It gives us a way to expand these. It kind of makes a code for this pattern so that we can use it for any binomial raised to any exponent. And then we'll do some examples with the binomial theorem. So the binomial theorem says that x plus y to the n power is the sum, so we know what this sigma means now, r equals 0 to n of NCR, and we'll talk about what that means in just a second, x to the n minus r, y to the r, where NCR, the other way we say this is n choose r, the other way that we write it is with parentheses, n factorial over r factorial times n minus r factorial. So the sum of the powers on our coefficients is always n. N minus r plus r is just n. And we're going to have, it turns out that this n choose r has the symmetry that we're looking for. We call this NCR, n choose r, are called the binomial coefficients. So our binomial coefficients, we want to have that symmetry that we saw in that pattern, and it turns out that this n choose r does have the symmetry that we're looking for. Can't go into the kind of all the details of where it all came from and how they figured it out, but this is what they figured out. So what I want to do first, I want to do some examples of calculating this n choose r. I will show you how to get to it on your calculator, and then we're going to use Pascal's triangle, which is what Nathan was asking about, and we talked about a little bit the other day, just briefly mention it, to shortcut this process. So I want to practice calculating these binomial coefficients, and then we will talk about how we're going to apply it to expanding some binomials. So if we had 10 choose 5, and the reason I say 10 choose 5 is it turns out that the binomial coefficients are also the number of ways to arrange 5 things out of 10. The number of combinations of 5 things out of 10. And when we start talking about probability, this 10 choose 5 will come up as well. And this is the same as, just so we have our symbols, this is the same as writing this. That's going to be 10 factorial over 5 factorial times 10 minus 5 factorial, which is 5 factorial. So to do this by hand, I'm going to write 10 factorial as 5 factorial times 6, times 6, times 7, times 8, times 9, times 10. Divided by 5 factorial times 5 times 4 times 3 times 2 times 1. 5 factorial here. Well, the 5 factorials cancel. I'm going to cancel that 5 with the 10 and I get a 2 there. I'm going to cancel the 4 with 8 and get a 2 there. A 3 with a 6 and get a 2 there. And a 2 with one of these twos. So I end up with 7 times 9 times 2 times 2. And when I multiply that out, I should get 252. So the binomial coefficient is 10, choose 5. This particular binomial coefficient comes out to be 252. Questions on what I did there? All right, let's look at another one. And then we'll talk about how we find these on our calculator. A choose 2 is the same thing as writing 8C2. All right, so 8 choose 2. So this is going to be 8 factorial over 2 factorial times 8 minus 2, which is 6 factorial. So to calculate this out by hand, I'm going to say this is 6 factorial times 7 times 8 divided by 6 factorial times 2 times 1. 2 factorial is 2 times 1. Well, those cancel. That 2 can cancel with that 8 and make a 4. And I get 7 times 4, and I get 28. So 8 choose 2, or this particular binomial coefficient is 28. The next one let's do in our calculator. So this is going to be 12C4. So let me get the calculator going here. So in your calculator, your NCR is in the math menu, and we're going to go over to probability. That's what the PROB means. So arrow over to probability, and then it's number 3. So if we want to do 12 choose 4, I'm going to clear out of there. I'm going to do 12, and then I go to over to probability, down to number 3. So there's 12, choose 4. I hit enter, and the calculator tells me that's 495. Yes? You have to put 12 in first. 12 in first, and then you go to the probability menu. And so I hit, so before I go there, I hit 12, and then I go to the menu. Whoops. So I hit random. Let me go back, delete that. So I put the number in first, and then go over to 3, and then put the second number in. All right, did everybody get it? So that's how we find these in our calculator. You should be able to do them in your calculator. You should be able to do them by hand as well, using the factorials. And we'll talk about a shortcut in just a little bit. So this comes out to be 495. All right, so let's use this binomial theorem to expand a binomial. So we want to expand 3 minus x squared to the 4th. I don't want to have to multiply these parentheses together 4 times. We could do it that way, but we want to use a binomial theorem. First thing I'm going to do here to make sure I keep everything straight is I'm just going to rewrite it as minus x squared plus 3. Now when you're doing these, and this is to the 4th power, when you're doing these, remember that the binomial theorem, going back, it's x plus y. So the signs have to stay with whatever number is inside our parentheses here. So the minus x squared, that negative sign has to stay with that x squared. The binomial theorem tells me that this is the sum, r equals 0 to 4, of 4, choose r, minus x squared to the 4 minus r times 3 to the r. And I'm letting r go from 0 to 4. So if I write that out before evaluating anything, so I'm going to write out all the pieces. So that's going to equal 4 choose 0 times minus x squared. This is when r equals 0. Minus x squared to the 4th times 3 to the 0 power. Plus 4 choose 1 times minus x squared. R is 1 now, so this is going to be 3, and times 3 to the 1 power. Plus 4 choose 2. Now R is 2. Minus x squared squared times 3 squared. Plus 4 choose 3 minus x squared to the 1st power and 3 to the 3rd power. And I have one more, I'm going to put it down here. Plus 4 choose 4 minus x squared to the 0 power and 3 to the 4th power. And then I'm going to calculate all of these, multiply by the 3 to the 0, 3 to the 1, 3 squared, 3 to the 3rd, 3 to the 4th, and then simplify. I'm not going to go through each calculation, but 4 choose 0. 4 choose 0 turns out to be 1. So this is 1 times minus x squared to the 4th. That's 1 times x to the 8th times 1. Minus x squared to the 4th is x to the 8th. Plus 4 choose 1 turns out to be 4 choose 1 turns out to be 4 times minus x squared to the 3rd. So I get a minus sign there. X to the 6th times 3. So the minus sign comes from the minus x squared to the 3rd. 4 choose 2 turns out to be 6. Minus x squared squared is x to the 4th. And 3 squared is 9. 4 choose 3 is, where am I at here? 6. 4 choose 3 is 4. And then I get a minus x squared to the 1st, so this turns into a minus sign. X squared, and then 3 squared is 27. And then 4 choose 4 is 1. And x squared to the 0 is 1. And then 3 to the 4th is 81. And then I simplify this, I get x to the 8th minus 12 x to the 6th plus 54 x to the 4th minus 108 x squared plus 81. So this is 3 minus x squared to the 4th, using the binomial expansion. So our symmetry in our binomial coefficients are here, 1, 4, 6, 4, 1. But then they get mixed up with this powers of 3, and that's why that symmetry doesn't show up in this last answer. And I only end up with even powers on x because this term is an x squared. So I'm always raising x squared to a power, so I only get even powers of x. Questions about what I did there? Now we could get to the same answer by multiplying these parentheses together, this thing together 4 times, and we would get to the same place. It's much easier if you had something to the 10th power to write out all these terms of the binomial expansion than it would be to multiply those parentheses together 10 times. All right, questions? Okay, a couple of things to be careful with. Let me look at, I'm not going to expand this next example, but I want to point out a couple of things. Let's say we had 3x minus y to the 4th. So, like I said before, the minus sign has to stay with this term. The 3 has to stay with this term. So this would be the sum, r equals 0 to 4, of 4c r, just like before, 4 choose r, 3x to the 4 minus r, times negative y to the r. And I would let r go from 0 to 4 and write out each term for this expansion. So I get a 3 raised to a power for each of these, and I get a negative 1 raised to a power for each of these. So you have to keep the signs and the numbers with each part when you do your binomial expansion. I'm going to do this really quickly. All right, so questions on this process. It's very mechanical. You just let r go from 0 to whatever your n is, and just go through the process of writing all those coefficients down, and all the variables and the exponents. And we're going to talk about a shortcut for these binomial coefficients in just a bit. All right, let's look at a couple of other kinds of problems that we might have to do. So we want to find the coefficient of x to the 8th in the expansion of x squared plus 2 to the 12th power. So if we were to do this the way the only way that we knew how before, we'd have to start multiplying all these parentheses out. We'd have 12 parentheses and figure out what the number was in front of x to the 8th. Well, with the binomial theorem, we can shortcut that. So I'm going to say that x squared plus 2 to the 12th power equals the sum, r equals 0 to 12 of x squared to the 12 minus r times 2 to the r. And we want the coefficient on x to the 8th. So first off, we need to figure out what r is going to be when we have our term x to the 8th. Well, this tells us our term, so we know that x squared to the 12 minus r has to equal x to the 8th. This is going to give us our 8th power of x. So if x squared to the 12 minus r equals 8, what does 12 minus r have to be? When I raise a power to a power, what do I do to my exponents? Multiply. So what do I have to multiply 2 by to get 8? 4. So that tells me that 12 minus r equals 4. So r equals 8. So all I have to do now is plug in r equals 8 to this formula. So the 8th term, the term where x to the 8th shows up. So the coefficient of x to the 8th is going to be I forgot something in my formula here. What did I forget? My 12CR. So let me back this up. I forgot that in our formula. So our coefficient is going to be 12C8 plus I'm going to get this number 2 to the 8th power multiplying that coefficient. Because r equals 8. So that's going to give us a number there. And when I find what 12C8 times 2 to the 8th power is, this comes out to be 126,720. So what this problem was really asking us, it was asking us for the coefficient, but what we had to do was find r, what r was for the binomial expansion for that particular term in the binomial expansion. So the number that's in front of the x to the 8th is this number. Questions on what we did there? All right, let's look at another type of problem. Let's find the 5th term. The 5th term in the expansion of 2x minus 3y to the 10th power. So we want the 10th term of the expansion in that thing. So I'm going to set this up exactly like I did the last problem. I'm going to say 2x minus 3y to the 10th equals the sum, r equals 0 to 10, and I won't forget my binomial coefficient this time, of 10CR, 2x to the 10 minus r, times minus 3y to the r. And we want the 5th term. So for the 5th term of that expansion, what is r? So this is kind of related to the problem that Daisy did on the board. Since r starts at 0, the 5th term is going to be when r equals 4. Because when r equals 0, I get the first term. When r equals 1, I get the second term. So for the 5th term, r equals 0. Or sorry, equals 4. So I'm just plugging r equals 4 into this expression. So the 5th term is 10 choose 4 times 2x to the 10 minus 4 or 6 power times negative 3y to the 4th power. And when I calculate all this out, I can find 10 choose 4, 2x to the 6th power, negative 3y to the 4th power. I end up with 1088, 640, x to the 6th, y to the 4th. So that would be the 5th term in that expansion. So, and I would kind of hate to have to multiply these parentheses together 10 times to get that term. All right, questions there? So all these problems with the binomial expansion come back to using this formula and either working with one part of it or writing out the entire expansion. All right, let's talk about a shortcut for these binomial coefficients. It's 10 choose 4. Pascal's triangle. Pascal's triangle is kind of an amazing thing. What we do for Pascal's triangle is we start with a 1 at the top. And there are always 1s on the outside edge. So the second row of Pascal's triangle is a 1 and a 1. Always start with a 1 on the outside. The number that we put here are these two added together. And I could keep going. So these are the first few rows of Pascal's triangle. Do these numbers, this 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, those look familiar? Those are the same numbers that were our coefficients when we expanded x plus y to the n. It turns out that Pascal's triangle is exactly that pattern that we were looking for. So I could rewrite this as 0 choose 0. 0 choose 1. Sorry, 0 choose 0. 0 choose 1. This row is 1 choose 0. 1 choose 2. 1 choose 1. And 1 choose 2. The third row is 2 choose 0. 2 choose 1, 2 choose 2, and 0, 1, 2 choose 0, 2 choose 1, 2 choose 2. What did I mess up here? Let me look at my drawing here. I have to remember my drawing. 2 choose 1. Sorry, this is 2 choose 1, 2. I did 0 twice, that's what I did. Sorry. So this is 0 choose 0. This is 1 choose 0. And 1 choose 1. There we go. This is 2 choose 0. 2 choose 1. And 2 choose 2. For that row. And this would be 3 choose 0. 3 choose 1, 3 choose 2, and 3 choose 3 for this row. So each of these rows are the binomial coefficients for the expansion when n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, etc. So these are the binomial coefficients when n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, etc., etc., etc. So this is a shortcut to finding those n choose r numbers. You can construct a Pascal's triangle. For the smaller numbers, it's pretty easy. For the bigger numbers, it gets a little tedious to keep going. but it works. So Pascal's triangle is kind of a nice little thing. Questions? A couple of other really cool things about Pascal's triangle. So what we can use it here for, just to backtrack a little bit, what we can use Pascal's triangle for is to find those binomial coefficients. This row tells us the binomial coefficients when n equals 0, when n equals 1, when n equals 2, n equals 3. So those are our binomial coefficients. So let me draw another Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So the outside edges are always 1. This second row are the counting numbers. 1, 2, 3, 4, 1, 2, 3, 4, 5. It'll keep going, 6, 7, 8. This third row, 1, 3, 6, are called the triangular numbers because they're the, if we stack things into triangles, those are called triangular numbers. The next row is called the tetrahedral numbers. So if we stack spheres on top of each other into little pyramids, these would be the number of spheres that would stack into a little pyramid. Couple of other things. Let's see. This first row, these are the powers of 11. 11 to the 0 is 1. 11 to the first power is 11. 11 squared is 121. 11 to the third is 1331. So these are powers of 11. If I add the numbers in the rows, this is 2 to the 0, 2 to the 1, 2 squared, 2 to the third, 2 to the fourth. So if I add the numbers in each row, I get the powers of 2. So that's another really cool thing that happens with Pascal's triangle. And I mentioned the other day Fibonacci sequence. If we take what we call the shallow diagonals of Pascal's triangle, I'm going to erase these powers of 11 here and the powers of 2. So we take what we call the shallow diagonals. There's 1. Take this this shallow diagonal. I get 1 again. I take the next shallow diagonal. I get 2 when I add those together. Take the next shallow diagonal. I get 3. Take the next shallow diagonal. I get 5. And there's Fibonacci sequence in Pascal's triangle. There's a lot of really interesting patterns that come up in Pascal's triangle. The main one that we can use in this section is these binomial coefficients. Pascal's triangle gives us binomial coefficients. All right, homework. And it turns out that you can get the number E out of Pascal's triangle also. It's a little more complicated, but it's another cool pattern that comes out. All right, there's homework. Guys, if you want, Mr. Evans came and told me that